Have you ever actually stopped to think about what really happens when you turn the key or, I guess these days, press the start button in your car? I mean, we use them literally every single day, yet we rarely think about the thousands of controlled explosions and rapidly moving metal parts firing in absolute perfect synchronization just a few feet away from us. Well, welcome to this explainer, where we're going to take a journey deep into the living anatomy of a machine.
I am so excited to guide you through our topic today, the anatomy of a machine, demystifying the automobile. Look, automotive engineering can seem incredibly dense. It's filled with complex physics, mechanical jargon, and honestly, some pretty complicated chemistry. But today, we're going to break it all down together. We'll peel back the metal and figure out how these incredible vehicles actually work, right from the ground up.
Okay, let's dive into this. Here is our roadmap for the explainer. We're going to explore the vehicle through 5 distinct anatomical systems. First, the skeleton, which is the chassis. Second, the heart, the internal combustion engine itself. Third, the lifeblood, covering cooling and lubrication. Fourth, the brain, looking at management and boost. And finally, the breath, understanding exactly how we filter emissions. Let's get right into it.
First up, Section 1, Skeleton, the vehicle chassis.
So before an engine can even run or a wheel can turn, a vehicle needs a foundational structure to hold the whole shebang together. But as you might guess, the skeleton you need to build a heavy, load-bearing truck is fundamentally different from the one you need for a fast, comfortable family car. For passenger vehicles, we primarily rely on a monocoque or unibody design. This just means the frame and the outer body are integrated into one single solid piece. It's a brilliant engineering choice for keeping weight down, getting better fuel efficiency, and it really enhances crash safety. But look over at the commercial side. Heavy vehicles, like massive delivery trucks, they almost exclusively use rigid ladder frames. They aren't prioritizing a soft ride. They need absolute, rugged durability to withstand massive payloads without buckling under the pressure. The takeaway here? A vehicle's skeleton is strictly dictated by what it's ultimately built to do.
Moving right along to Section 2, Heart, the internal combustion engine.
This right here is where the true mechanical magic happens, transforming chemical energy into violent, kinetic motion. This fundamental 4-stroke cycle is the heartbeat inside most car engines. It's a crazy fast, continuous sequence. First is intake, where a cylindrical piston moves down, sucking a fresh fuel-air mixture into the chamber. Second is compression. The piston pushes back up, squeezing that mixture incredibly tight. Then, power. A spark plug ignites the highly pressurized charge, causing a massive, rapid expansion that slams the piston back down. And finally, exhaust, where the burned gases get pushed out to clear the room for the next round. The absolute genius of this is in the mechanical linkage. The piston just moves up and down, but it's attached to a connecting rod, which turns a crankshaft. That simple connection converts those violent up and down explosions into the smooth, rotary motion that eventually turns your wheels.
Now, the scientific principle driving that mechanical heartbeat, that's called the Otto cycle. Proposed way back in 1862 by Nicholas Otto, it perfectly describes this exact process for spark-ignition petrol engines. The Otto cycle is actually known as a constant volume cycle. Why? Because the combustion happens so incredibly fast that the volume of the gas barely has time to change during the explosion itself. This is really distinct from heavy commercial vehicles that use the diesel cycle. Diesel engines rely on super high compression to self-ignite the fuel at a constant pressure, which gives them that massive low RPM pulling torque. But for our everyday passenger cars, the Otto cycle's rapid 4-stroke rhythm is the gold standard.
Which brings us to Section 3, Lifeblood, Cooling and Lubrication.
Containing thousands of tiny, violent explosions every single minute creates 2 massive threats to our machine: intense heat and destructive friction. To solve the heat problem, engineers basically use 2 main tricks. First, air-cooled systems. These just use metal fins along the outside of the engine block to conduct heat right into the passing air. It's super simple, very lightweight, and it literally can't leak, which is exactly why you see it on smaller engines like motorcycles. But for the crazy heat generated by a heavy car or truck, just blowing air over some fins isn't going to cut it. That's where the water-cooled system steps in. This is a complex network where a pump circulates water or coolant through jackets built right inside the engine walls. That liquid absorbs the heat, carries it away to a radiator where a fan cools it down, and then continuously recirculates.
But liquid cooling is only half the lifeblood equation. The other half is lubrication. Engine oil is, without a doubt, the true unsung hero of the automobile. Beyond the obvious job of reducing friction between metal parts, it does so much more.
It creates a tight seal around the piston rings to trap those high-pressure combustion gases. It cleans away destructive carbon particles. It actually acts as a cushion to absorb mechanical shock between bearings. And it even helps cool heated surfaces from the inside out. Whether it's a standard wet sump system pooling oil at the bottom or a fancy high-performance dry sump system pumping it from a separate tank, this slippery liquid is the only thing keeping the engine from completely tearing itself apart in a matter of seconds.
All right, let's move to Section 4, Brain Management and Boost. So, now that our engine is structurally sound, running smoothly, and protected from heat and friction, how do we make it smart? Here's a huge engineering challenge the industry has faced for decades. How do we get big power from a small engine? Historically, if you wanted more horsepower, you literally just built a bigger, heavier engine. But as you can imagine, a heavy engine ruins your fuel economy and makes the car handle like a boat. Modern engineering asks a way better question. How can we extract massive performance from a compact space without just adding bulk? Modern vehicles solve this by using electronic control units, the ECU, alongside some incredibly clever mechanical tricks.
And the answer largely lies in how the engine breathes, specifically through variable valve timing, or VVT. See, in older traditional engines, the valves that let air in and push exhaust out operated on strict, fixed schedules. But VVT changes the game. It's a technology that actively alters the timing, and sometimes the lift, of the valves while the engine is actually running. It uses electronic solenoids and engine oil pressure to rotate a cam phaser, slightly advancing or retarding the camshaft. Basically, it allows the engine's brain to dynamically change its breathing pattern based on exactly how fast the engine is spinning.
And this brilliantly illustrates the real-world "so what" of the technology. The advantages are absolutely massive. Because the valves can physically adjust, VVT can advance timing to increase your low RPM pulling torque when you're taking off from a stoplight. Then, if you floor it onto the highway, it alters the timing again to boost your high RPM horsepower. All while improving fuel efficiency when you're just cruising along, and even reducing harmful NOx emissions by controlling valve overlap. It's the ultimate have your cake and eat it too solution. Muscle exactly when you need it, and efficiency when you don't.
Which leads us perfectly into our final anatomical system, Section 5, Breath, Emissions, and Control.
After all that power is made, what exactly is the vehicle exhaling, and how do we manage those toxic chemical reactions before they hit the open air? Now, what's really interesting about this slide is the sheer scale of the problem. Out of all the primary pollutants emitted by road vehicles by weight, carbon monoxide accounts for a staggering 91%. Why is it so high? Well, because internal combustion engines aren't perfect. Combustion is often incomplete, especially when a car is just idling or slowing down. Without enough oxygen to fully convert the carbon into harmless carbon dioxide, we're left with highly toxic carbon monoxide escaping directly into the exhaust. But actually, unburned fuel isn't the only headache. Sometimes the engine is actually too efficient at creating heat, which triggers this wild chemical process called the Zeldovit chain reaction. The air drawn into an engine is mostly nitrogen, which normally just passes right through harmlessly. However, when we push an engine to its absolute peak combustion temperatures, that immense heat physically breaks down oxygen and nitrogen molecules, causing them to bond together. This forms oxides of nitrogen, or NOx, a seriously dangerous secondary pollutant. So ironically, making the engine burn hotter and more powerfully inadvertently creates an entirely new chemical hazard.
And then we have the architectural quirks of the engine itself, like a phenomenon known as flame quenching. Inside the combustion chamber, the cylinder walls are actively cooled by that water cooling system we talked about earlier. Because those metal walls are relatively cold, they create this microscopic dead space right next to them. When the spark plug fires and the fireball rapidly expands, the flame is literally quenched, or put out, the second it hits this cold boundary. The fuel trapped in that tiny space fails to burn, which means raw, unburned hydrocarbons just get scraped up by the piston and shoved right out the exhaust valve.
So, to combat all of these chemical issues, modern vehicles act as their own filtration organs, using 3 incredibly clever management systems. First is the PCV system. This captures blow-by gases that sneak past the piston rings and loops them right back into the intake to be burned again safely. Second, the EVAP system. This acts like a trap, storing evaporating fuel tank vapors in a charcoal canister so they don't drift away, and later feeds them into the engine while you drive. And third, the legendary catalytic converter. This is basically a ceramic honeycomb coated in precious metals sitting in your exhaust pipe. It acts as an on-the-go chemical lab, rapidly oxidizing those toxic hydrocarbons, carbon monoxide, and NOx into harmless water, nitrogen, and carbon dioxide before they ever reach the tailpipe.
The big takeaway here is that a vehicle's emissions control isn't just one static part. It's a constantly evolving ecosystem, and it's been heavily driven by strict pollution control mandates over the decades. By mandating the removal of harmful lead from petrol, requiring those catalytic converters by law, drastically reducing sulfur in diesel fuel, and eventually phasing out older, highly polluting vehicles, regulations have literally forced automotive engineering to rapidly adapt. The result? A far cleaner, infinitely more sophisticated vehicle anatomy today than we had even 20 years ago.
Which brings us to the very end of our journey today and leaves us with a massive, provocative question. As engineering perfectly refines the internal combustion engine to its absolute physical limits, what will power the anatomy of our future vehicles? Will the mechanical heartbeat of pistons and crankshafts be entirely replaced by the silent hum of electric batteries? Or maybe hydrogen fuel cells? The physical anatomy of the automobile is shifting faster right now than at any point in history. It is a thrilling time to understand exactly how these machines work, and honestly, even more exciting to imagine what they're going to become tomorrow. Thank you so much for joining me on this explainer. Keep wondering.